This is my intermediate algebra course. Today we're going to continue to learn functions and function notation. If you haven't done the homework completely and correctly from last class, do that homework before watching this video. Today we're going to learn how to find the domain of a function. But before we do that, let's discuss the general idea of domain. And I'm going to use two examples that we presented in a previous class. If you're playing a video game, the console is the function, and the buttons that you push on your controller, those are the inputs of the function, and the outputs, of course, are anything that your player does on the screen. So you put in an input, you push a button, your console processes that input and spits out an output, meaning your player does something on the screen. In the example of the car, you put in an input, which is turning the steering wheel right or left. The function, which is the mechanics in the car, the axle and the joints, they process the input, and whatever your car does as a result, whether it be turn right or left or skid around, that's the output. So everything that you can do on the controller that produces an output, every button that you can push, all those buttons together are called the domain of the function. And everything that your player does as a result of pushing those buttons, whether it be move forward or jump up or fly in the air, whatever your man can do, all those things together that your player can do on the screen is called the range of the function. For example, you might say, I just bought this new video game and you can do all kinds of things with the game. It has a large range of things that it can do. That kind of relates to the mathematical definition of range. And of course, all the possible angles that you can turn right or left of that steering wheel, that's called the domain of this example, using the car as an example. And everything that that car does as a result of turning that steering wheel, all the possible things that that car can do are called the range of the function. Now, we're not going to talk about range today. We're going to leave that for a future class. We're just going to focus on domain. So domain is all of the inputs of a function that are able to produce an output. Now notice that it says the inputs that are able to produce an output. I just want to mention real quickly that sometimes there's a button on your controller that doesn't actually do anything. It's not programmed to do anything. So when you push that button, it doesn't actually produce an output on the screen. Any button that doesn't do something, that's actually not part of the domain. Only the buttons that actually create an output are part of the domain. So using the car as an example, if you took this steering wheel and ripped it off the car, well, the car doesn't really know how to interpret that. It's not really going to put out an output. So that's not part of the domain of this hypothetical example. Now, when it comes to these examples, it's pretty easy to understand the domain. It's not something that's really that difficult. You can turn the steering wheel left or right. You can push, whatever buttons are on your controller that produce an output. The domain is pretty easy to understand. But when it comes to mathematical functions, it's not as easy to understand for the simple reason that usually mathematical functions have an infinite number of possibilities for your inputs. For example, the first function that we're going to analyze here is 1 over x. You can actually plug in an infinite number of inputs. You can plug in 5 and you get your output, which is 1/5. You can plug in 1,000 and your output is 1 over 1,000. You can plug in a trillion, you can plug in negative a trillion, you can plug in fractions, you can plug in roots, you can plug in an infinite number of possibilities. And for that reason, it's not as easy to think about the domain of mathematical functions because there's just so many possible inputs you can plug in. So in many cases, it's actually easier to think about what the inputs cannot be rather than what they can be. There's an input, a number, that if you plug it into this function, you're actually going to get an undefined output. There's just one number, only one number that we cannot plug in to this function. That number is 0. If we plug in 0, we get 1 over 0. This expression is actually undefined. Now, I want to do a little review here. 0 over 1, that's actually defined. For example, if you had a pizza and you cut it into 8 parts and then you ate the entire pizza, then you would have 0 out of 8 parts, which is 0. That actually means something. 0 over 1 is 0. Whenever you have 0 in the numerator and a different number in the denominator, that expression is equal to 0. That has meaning. So you can plug in 0 into a numerator of a fraction, that's okay. But if 0 is in the denominator of a fraction, if you have 1 over 0, that expression is actually undefined. That doesn't mean anything. So if you plug in 0 into this function, it will produce an undefined output. It's like pushing a button on your controller that doesn't actually make your player do something on the screen. That's not part of the domain. So the domain is all numbers except 0. So it says in these problems, find the domain of each function below and explain your reasoning. So we found the domain. The domain is all numbers except 0. You can plug in any number in there as long as it's not 0. That's all the possible inputs that you can plug in there. And the reasoning behind that, because it says we have to show the reasoning, right? The reasoning behind that is a fraction with 0 as its denominator is undefined. Sorry about my writing, I'm trying to write kind of fast here. A fraction with 0 as its denominator is undefined. So again, the domain, all the inputs that we're allowed to plug into this machine, those inputs are all numbers except 0. Now, there's one more complication that we have to add here. Notice that I said all numbers can be plugged into the function except 0. But here's the problem. Notice up here in red it says neither imaginary nor complex numbers are allowed to be inputs or outputs of functions. So mathematicians will get kind of angry if you say all numbers, because imaginary numbers, those are considered to be numbers also. But we're not allowed to plug in imaginary numbers into functions. So if we say all numbers, that includes imaginary numbers. So we have to be more specific, or mathematicians get angry. We have to say all real numbers, meaning no imaginary numbers, no complex numbers. I know that's kind of tedious to have to use that adjective every time, but I just want you to get used to the way mathematicians write things, because that's how you're going to see it, and that's how you're going to be expected to write that. So let's try another example. We're going to find the domain of this function. That's the purpose of these problems. Again, we're finding the domain of each function, and we're explaining the reasoning behind it. So I've written out the explanation here because I don't want you to have to watch me do that every time. So a fraction with 0 as its denominator is undefined. We cannot have 0 in the denominator, remember that? So what that means is that x minus 4 cannot be 0. All right? If x minus 4 is 0, then you're not going to get a defined output. So I'm going to set x minus 4 equal to 0 and solve this equation to find the input, the x value, that you would plug in to make the denominator 0. So if we add 4 to both sides, we see that if we plug in 4 into this function, we're going to get 0 on the denominator. So 4 is an input. If you plug in that input into this function 4, you're going to get negative 7 over 0, and that's not going to produce an output. So the domain is all real numbers. Remember, we have to say real numbers because imaginary numbers are not allowed. All real numbers except 4. So again, the domain is an infinite number of values that we can plug in there. But there's one value we're not allowed to plug in. So what I'm going to do is I'm going to actually go back to this equation, and I'm going to say that we don't want x minus 4 to be 0. We don't want x to be equal to 4. So instead of saying it's an equation, it's kind of a, we don't want it to be equal to 4. You don't have to do that if you don't want to, but I just like writing that because we're explaining what x cannot be. So we can, again, just to be clear here, we can plug in any real number into this function. That's the domain, except 4. So the domain is all real numbers except 4. Let's try one more of these problems. I know this is kind of confusing. Domain is a little confusing, but you're going to get used to this as we do more problems. So again, we're going to try to find the domain of this function, all the possible inputs that will produce an output. But again, because this is a fraction, we can't have 0 in the denominator. A fraction with 0 as its denominator is undefined. So what that means is that 2x plus 10 cannot be 0. So I'm going to set 2x plus 10 equal to 0 because I'm going to try to figure out what values of x would make 2x plus 10 equal to 0, and I'm going to exclude those x values. In this case, it's just going to be one x value. I'm going to exclude those x values from the domain. So subtract 10 from both sides and divide both sides by 2, and we have negative 5. So we do not want x to be equal to negative 5, so the domain of that function is all real numbers. Again, you want to say real numbers, imaginary numbers are not allowed. All real numbers except negative 5. So again, we have a machine, a function. We want to know all the inputs that we can plug into that function that will produce an output. We can plug in any real number into that input. There's an infinite number of possibilities, but there's one value that we can't plug in. We cannot plug in negative 5 because that will not produce an output. 1 over, or in this case, 5 over 0, that has no meaning. Okay, so I want you to try number 4. You can use numbers 1 through 3 to help you. And remember, I want you to write the reasoning behind your answer. So try number 4. When you come back, we'll do it together. All right, we're back. So I don't want you to have to watch me write the reasoning out, so I've already gotten it written out here. Remember, a fraction with 0 as its denominator is undefined. So what that means is that x plus 10 cannot be 0. So I'm going to try to figure out the x values that make that expression 0, and of course we just solve. And we don't want x to be negative 10, because if you plug in negative 10 for x, you get 1 over 0. So the domain is all real numbers. Make sure you write all real numbers. All real numbers except negative 10. Again, we're not allowed to plug in imaginary numbers into a function. So we can plug in any x value into this function that counts as an input, except negative 10, because if you plug in negative 10, you get 0 in the denominator, and that's not an output that the function can recognize. So if you got that answer, good job. So you can take a picture with your phone of these problems to help you with number 5 if you want to. And I want you to go ahead and try number 5, and when you come back, we'll do it together. All right, we're back. So rather than you having to watch me write the reasoning. I'm just going to bring that out here. A fraction with 0 as its denominator is undefined, so what that means is that 3x cannot be 0. So I'm going to set 3x equal to 0 and say I don't want it to be 0. Divide both sides by 3, and we see that if x is equal to 0, then that will produce negative 4 over 0, which is not a recognizable output. So 0 is not part of the domain. So the domain is all real numbers, because we can plug in any other x value. There's an infinite number of x values that we can plug in, inputs to that machine, that function. But we cannot plug in 0. So all real numbers except 0. If you got that answer, good job. Remember, I want you to show the explanation. I know it's kind of tedious to have to write this out. We're not going to write out the explanation for every problem today, but just to get started here with the general idea of domain, I want you to go ahead and show an explanation. So if you got that answer, good job. Go ahead and try number 6, and when you come back, we'll do it together. All right, we're back. So again, I don't want you to have to watch me write all that stuff out, so I'm just going to bring out the explanation here, the reasoning. We're not allowed to have 0 in the denominator, so what that means is that 5 minus 9x cannot be 0. So any x value that you plug in that is going to make that denominator 0, that can't be part of the domain of the function. So we're going to figure out what x values make 5 minus 9x equal to 0. So I'm going to subtract 5 from both sides, divide both sides by negative 9, and we end up with 5/9. So again, we don't want x to be equal to 5/9. So our domain is all real numbers except 5/9. Okay, so if you plug in 5/9, you get 0 in the denominator. So our domain, 5/9 is not part of the domain. If you got that answer, good job. Now we're going to go to a different type of function. Notice that all the previous problems we were dealing with fractions with a variable in the denominator. But before we go into the next type of function, let's review inequalities. Remember, to solve an inequality, you just treat it like an equation and solve like normal. Pretend that this is an equal sign. I'm going to add 1 to both sides, divide both sides by 2, and we get 2 is greater than x. So that is the solution of the inequality. So basically all we're doing is just taking this expression and simplifying it, so we see that any x value that is less than 2 is going to make this inequality true. It's the same statement, just a simplified version. So let's try another example. Again, I'm just going to isolate x as we normally would in an equation. I'm going to subtract 5 from both sides, and then multiply both sides by negative 3. And notice when I multiply both sides by negative 3, I'm actually going to flip the inequality. Remember, when you multiply or divide both sides of an inequality by a negative number, you have to flip the inequality. When you multiply or divide both sides of an inequality by a negative number, you have to flip that inequality. So our answer is x is greater than or equal to 9. So go ahead and try example 3, and when you come back, we'll do it together. All right, we're back. So I'm going to subtract 6 from both sides and divide both sides by negative 5. And we have x is less than or equal to negative 2. So remember, when you divide by negative 5, you have to flip that inequality. We divided by a negative. If you got that answer, good job. Go ahead and try example 4, and when you come back, we'll do it together. All right, we're back. I'm going to subtract 8 from both sides. Now I'll multiply both sides by 4. So if you got that answer, good job. So now let's try this different type of function here. Notice we have a square root. We're going to be dealing with functions that have square roots and variables inside those square roots. Now when it comes to a square root, remember we're not allowed to have a negative number inside a square root because that's actually it's defined as an imaginary number. And we don't really have to go into depth, about why exactly that is right now, but remember the square root of, let's say, 9, that's just asking what number times itself is 9. Well, obviously 3 times 3 is 9. But what if you ask, what is the square root of negative 9? What number times itself is equal to negative 9? Well, there is no number. If you multiply a positive by itself, you get a positive. If you multiply a negative by itself, you also get a positive. A negative times a negative is a positive. So there is no square root of negative 9 unless you want to define it as an imaginary number. So we're not allowed to have a negative under a root because that produces an imaginary output. Remember, we're not allowed to have imaginary numbers for inputs or outputs. So again, sometimes it's better to think about what the domain cannot be rather than what it can be. If x is any negative number, then we get an imaginary output. So the domain is all real numbers greater than or equal to 0. Now you might be thinking, whoa, wait a second, 0, we can't plug in 0. Well, actually, 0 is fine. The square root of 0 is just 0. What number times itself is equal to 0? Well, 0 times 0 is 0, so that works, that's fine. So any number that is greater than or equal to 0, so 0 or any bigger number will work. But if you plug in anything less than 0, a negative number, then it's going to produce an imaginary output. So what is the explanation? What is the reasoning behind that? The square root of a negative number is imaginary. It's an imaginary number. In fact, I'm going to reword that a little bit. The square root of a negative number is an imaginary number. So x must be greater than or equal to 0. Sorry about the writing there. All right, so let's try another one of these problems. And again, that's the domain of the function. You want to figure out what are all the inputs that we can plug into this function that will produce an output. You can plug in any number 0 or greater and it will produce an output. But if you plug in a negative number to this machine, this function, that'll produce an imaginary output, and we're not allowed to have imaginary outputs for functions. Now you might be thinking to yourself, well, why is that? Why can't we have imaginary outputs? Well, mathematicians have just decided that. They've just decided that they're not going to allow imaginary outputs. All right, let's try another problem here. I've written down the reasoning here so you don't have to watch me do that. The square root of a negative number is an imaginary number. So what that means is that whatever's inside that root, in this case 5 minus x, it must be greater than or equal to 0. So what we want to do is we want to find the inputs, the x values, that you plug in here that will make this either equal to 0 or greater than 0. So this is a little different from the problems that we did before. We were trying to figure out what to plug in we were trying to figure out what we could not plug in to make the denominator 0. But here we're doing things a little different. We're trying to figure out what we can plug in to make this function work. So we want 5 minus x to be greater than or equal to 0. If we solve this inequality, that's going to give us all the values that we can plug in to the function, the domain. So I'm going to subtract 5 from both sides and divide both sides by -1. And remember, whenever you divide an inequality by a negative, you have to flip the inequality. So there you go. That's the domain. Again, be aware that in the previous problems with fractions, we're trying to figure out what x could not be. In this problem, we're trying to figure out what x can be. So you need to realize that. Don't be confused by that. So x can be all real numbers. Again, we're not allowed to have imaginary inputs. Our inputs can be all real numbers less than or equal to 5. Okay? So if you plug in any number that is less than or equal to 5 into this machine, you're going to get an output. But if you plug in any number that's greater than 5, you're going to get a negative under the root. We're not allowed to do that. You're going to get an imaginary output. Again, I know this stuff seems very strange, but you're going to get the hang of it as we do more practice problems. So number 9, again, I don't want to write all this stuff out and bore you, so I've gotten it written out for you. The square root of a negative number is an imaginary number. So 2x plus 1 must be greater than or equal to 0. So we want to find the x values, the inputs that we can plug in to make 2x plus 1 greater than or equal to 0. So we set up this inequality and solve it, and that will tell us what x values we can plug in to make the number inside the root positive. So I'm going to subtract 1 from both sides, divide both sides by 2, and I'm not dividing by -2. I'm not dividing both sides of the inequality by a negative. I'm dividing by +2, so you don't flip the inequality. So the domain, as you can see, any number that we plug in that is equal to -1/2 or greater than -1/2 will make this number positive. So all these numbers greater than or equal to -1/2 are part of the domain of the function, the inputs that we can plug in. So the domain is all real numbers greater than or equal to -1/2. Okay, so I want you to try number 10. You can use number 9 to help you. You must show your reasoning, write your reasoning out, and you're going to write an inequality and solve that inequality. Again, you want whatever's inside the root to be greater than or equal to 0. So set that up, Again, you want whatever's inside the inequality to be greater than or equal to 0. So you're going to set that inequality up and solve it. So try number 10, and when you come back, we'll do it together. All right, we're back. So I'm going to bring this reasoning out for you so you don't have to watch me write that. The square root of a negative number is an imaginary number. So -1 plus x must be greater than or equal to 0 because we're not allowed to have imaginary outputs. So -1 plus x must be greater than or equal to 0. Set up your inequality. Then we're going to solve that inequality. Add 1 to both sides, and we're done. So again, as opposed to the first problems that we did with fractions, these problems talk about what x can be. Sometimes it's better to ask what x can be, the inputs can be. Other times it's easier to think about what the inputs cannot be. It just depends on the function. I know that's kind of confusing, but the domain is all real numbers. Again, we're not allowed to plug in imaginary numbers as inputs or outputs. all real numbers greater than or equal to 1. So if you got that answer, good job. I know this stuff is very strange, but again, with more practice problems, you'll get used to this. So I want you to try number 11, and when you come back, we'll do it together. All right, we're back. So again, I don't want you to watch me have to write all the reasoning out, so I'm going to bring that out. The square root of a negative number is an imaginary number, so negative 6x must be greater than or equal to 0. So I'm going to set up that inequality and solve the inequality to see what x values will work. I'm going to divide both sides by negative 6, and because I'm dividing both sides of an inequality by a negative, I have to flip that inequality. And so we see that the domain must be all real numbers less than or equal to 0. So if you plug in any input that's less than or equal to 0, you're going to get a recognizable output. But if you plug in any number that's greater than 0, you're going to get an imaginary output, which is not allowed. Our function doesn't know how to process that. All right, so if you got that answer, good job. Go ahead and try number 12, and when you come back, we'll do it together. All right, we're back. So again, I don't want you to have to watch me write out the whole reasoning, so I'm going to make that appear on the screen. The square root of a negative number is an imaginary number, so 5 minus x over 7 must be greater than or equal to 0. So what are the x values that would make that true? Well, we're going to set up an inequality and solve the inequality, and that'll tell us the x values that will make that statement true. Multiply both sides by negative 7, and remember, because you're multiplying both sides by a negative, you have to flip the inequality. So we see that the domain is all real numbers less than or equal to 35. So if you got that answer right, good job. Okay, now we're going to a third type of function, logarithms. Now remember, we learned in our lessons on logarithms that this value inside the logarithm is not allowed to be negative or 0. And we could go into a lengthy explanation of why exactly that is, but that might take a while, and we'll have to do a bunch of review of logarithms, and so we can worry about that later. But you can go back to my classes on logarithms, and I'll explain why you're not allowed to have a negative number in there. But it's not going to produce an output if you plug in a negative number. And 0 also doesn't work. If we plug in 0 here, that's not going to produce an output. So the domain is all real numbers greater than 0. All real numbers greater than 0. So what is the reasoning behind that? The reasoning is both 0 and negative numbers produce an undefined logarithmic expression. So x must be greater than 0. Both 0 and negative numbers produce an undefined logarithmic expression, So x must be greater than 0. So again, the domain of that particular function is all real numbers greater than 0. If you plug in a number greater than 0, you're going to get an output. If you plug in a number less than 0 or equal to 0, it's not going to produce a recognizable output in that function. So let's try another one of these. I have the reasoning written out for you. So both 0 and negative numbers produce an undefined logarithmic expression, so x plus 7 must be greater than 0. So again, we can just set up an inequality here. X plus 7 must be greater than 0. It can't be equal to 0, it's got to be greater than 0. So solve that, and we see that any value that is greater than negative 7 is going to be part of the domain, all the possible inputs that you can plug in. All real numbers greater than negative 7. So again, the domain is all the possible inputs that will produce an output. As long as you plug in an input that is greater than negative 7, it'll produce an output. So the domain is all numbers greater than negative 7, all real numbers. So again, we're using inequalities here to solve these problems. So let's find the domain of this function. Again, the reasoning is both 0 and negative numbers produce an undefined logarithmic expression. So 4 minus x over 2 must be greater than 0. So we're going to set up an inequality and solve that inequality. Multiply both sides by negative 2, and when you do that, you have to flip the inequality. And the domain is all real numbers less than 8. All right. So now it's time for you to try. Go ahead and try number 16. Remember, write your reasoning and state the domain. You're going to have to set up an inequality. So try 16, and when you come back, we'll do it together. All right, we're back. So I'm going to pull out this reasoning so you don't have to watch me write that. Again, we're not allowed to have 0 or negative numbers inside this, excuse me, we're not allowed to have a negative number or 0 as this whole number here. So 9x must be greater than 0. So set up an inequality, solve the inequality, and we see that the domain is all real numbers greater than 0. So if you got that answer, good job. Go ahead and try number 17, and when you come back, we'll do it together. All right, we're back. So again, I don't want you to have to watch me write that whole reasoning, so I'm just going to bring it out here. And we say both 0 and negative numbers produce an undefined logarithmic expression, so x minus 1/2 must be greater than 0. So I'm going to set up an inequality and solve the inequality. And so we can see the domain must be all real numbers greater than 1/2. So if you got that answer, good job. You can take a picture of these problems with your phone if you want to use those to help you do number 18. So go ahead and try number 18, and when you come back, we'll do it together. All right, we're back. So both 0 and negative numbers, again, produce an undefined logarithmic expression. So negative x over 4 plus 8 must be greater than 0. So let's set up our inequality to figure out what x values would make that true. So we're going to subtract 8 from both sides and multiply both sides by -4. And when you multiply both sides of an inequality by a negative number, you have to flip the inequality. So we see that the domain is all real numbers less than 32. So again, if we plug in a number equal to 32 or greater than 32, we get a negative number, or 0, as this green number here, and that produces an undefined output. So if you got that answer, good job. So now we're going to go to piecewise functions. Finding the domain of piecewise functions is actually really easy. Remember, a piecewise function is a function that has multiple expressions, and you're told when to use those expressions with this inequality notation. When x is between 4 and 8, then you plug it into this expression to get your output. When your input, or your x value, is between 9 and 13, then you plug in that input into this expression to get your output. But remember, with a piecewise function, these inputs are the only inputs that are allowed to be plugged into the function. All other inputs do not produce a defined output. That's just the way that piecewise functions are defined. So in the case of piecewise functions, you can actually see the domain. It's actually written right next to the expressions. So the domain is all real numbers between 4 and 8, that's up here, or, it's very important that you say or, and I'm going to explain why later, or between 9 and 13. So all real numbers between 4 and 8, or between 9 and 13. Or means that your input has to be in this interval, or it has to be in this interval, but not both. It can't be between 4 and 8 and 9 and 13 at the same time. So instead of using the word and here, you want to say or. That's very important. So what is the reasoning behind that? Well, let's see the reasoning. The reasoning is, this is a piecewise function, so the accepted inputs, i.e. the domain, are described with inequality notation alongside the function. That's this inequality notation here. So all we have to do is look at that inequality notation, and it tells us the domain. Again, we're not allowed to plug in any other values. Only these values are allowed and defined. They're the only values that produce an output. So let's try one more of these. We can see the domain is right next to the expressions. Again, the domain is all real numbers between -5 and 7, or your inputs can be between 10 and 23. Again, it's very important that you use the word or. Your input cannot be between -5 and 7 and between 10 and 23 at the same time. It can be one or the other. So all real numbers between -5 and 7, or between 10 and 23. So finding the domain of piecewise functions is really easy, because the domain is actually written right next to the expression. So try number 21. When you come back, we'll do it together. All right, we're back. So again, it's the same reasoning. So the domain is written in inequality notation, so we know it must be all real numbers between negative 62 and negative 40, or between 0 and 86. So if you got that answer, good job. Go ahead and try number 22, and when you come back, we'll do it together. All right, we're back. We have the same reasoning. Sorry, my computer's going kind of slow here. It's a piecewise function, so the accepted inputs are described with inequality notation alongside the function. So the domain is all real numbers between 2 and 4, or between 7 and 12. If you got that answer, good job. So now we're going to a slightly different type of problem. We still have piecewise functions, but notice we have less than or equal to symbols. So the domain for this function would be all real numbers between negative 8 and 4, but then we put a comma and we say inclusive. What does that mean? Well, that means our inputs can be any number between negative 8 and 4, but also we can plug in negative 8 itself and 4 itself. Or the domain is, we can say, or all real numbers between 6 and 37 inclusive. So again, we say inclusive because these inequality symbols are less than or equal to symbols also. So the difference with those problems is that we're saying inclusive. It can include 6 and 37 or negative 8 and 4, and also those numbers between them. So here's another example. So the domain in this case is going to be a little different, because notice that these two numbers are the same. So this is actually describing an interval that is connected. So you start at 0 and you go to 9. In between we have 3, but the interval, it's not broken as it was in the previous problem. So if you describe this interval, we start at negative 8 and you go to 4, and then you start at 6 and you go to 37. I know it's not equal spacing, but you get the point. So there's a break in between. But in this problem down here, and maybe I should just keep that up there, there is no break in the interval. So it's much easier to write the domain in this case. It's just all numbers between 0 and 9, and including 9. Sorry, my computer's going kind of slow. So we say the domain is all real numbers between 0 and 9, comma, including 9. Now, we didn't say inclusive. Instead of saying inclusive, we said just including 9, because 0, notice that x can be greater than 0, but it can't be equal to 0. if we had a less than or equal to symbol here and here, both the symbols were less than or equal to, then we would just say inclusive, and that would mean 0 and 9. But because only 9 is allowed to be part of the inputs, we say all numbers between 0 and 9, including just 9, not including 0. Then we'd say inclusive. So I want you to try number 25, and when you come back, we'll do it together. All right, we're back. So the reasoning is the same reasoning. We see the domain at the right of the function, so all real numbers between 4 and 12. And notice that these are all less than or equal to symbols. So we have to say all real numbers between 4 and 12 inclusive, meaning including 4 and 12. Our inputs can be 4 and 12 also, along with the numbers in between those. So all real numbers between 4 and 12 inclusive, or all real numbers between 13 and 15 inclusive, because again we have less than or equal to symbols on the 13 and the 15. So numbers between 13 and 15, but also including 13 and 15. So if you got that answer, good job. Go ahead and try number 26, and when you come back, we'll do it together. All right, we're back. So again, same explanation. This is a piecewise function, so the accepted inputs are described with inequality notation next to the expressions. So the domain is all real numbers between -4 and -1. But in this case, notice that these two numbers are actually the same. So it's actually going to be a lot easier to write the domain. It's going to be between -4 and 6, because it's a connected interval. We go from -4 all the way to 6, and there's no breaks in between. And it says less than or equal to -4, but it only says less than 6. So our domain includes -4, but not 6. So we say all real numbers between -4 and 6, including -4. So if you got that answer, good job. Okay, we have one more type of piecewise function here. The domain for this one would be all real numbers. And notice that our interval is connected. We go from 100 to 700, no breaks in between. But we don't have any less than or equal to symbols, only less than symbols. So the domain is all real numbers between 100 and 700. That's all you have to write. All right, so looks like we have the same situation here. So the domain is all real numbers between -10 and 87, and that's it. Again, we don't have less than or equal to symbols for -10 and 87. So our domain is all numbers between -10 and 87, but not including -10 or 87. So why don't you try number 29, and when you come back, we'll do it together. All right, we're back. So again, we have the same reasoning. It's a piecewise function, so the domain is written right next to those expressions. And it looks like we don't have any breaks in the interval, so all real numbers between -1 and 17, but not including -1 and 17 because we don't have less than or equal to symbols, only less than symbols. Alright, so if you got that answer, good job. Go ahead and try number 30, and when you come back, we'll do it together. Alright, we're back. So again, we don't have any breaks in the intervals. So all real numbers. The domain is all real numbers between 0 and 14. But not including 0 and 14, only the numbers in between those. So if you got that answer, good job. Now it's important to understand that there are some functions that actually have no domain restrictions. So far we've focused on functions that do have significant restrictions. But in the case of a linear function, you can plug in any real number. As long as it's a real number, you can't plug in imaginary numbers for inputs or get imaginary numbers for outputs. But any real number will produce an output. So we can say that the domain is all real numbers. And that's it. And the reasoning that you can give for that is the following. The function has no square roots, fractions, logarithms, or other things that might restrict its domain. That's the only explanation that I really require at this point. So here's some other examples. If you plug in any real number, you're going to get an output. You can try it. There's no fractions with variables in the denominator. There's no square roots. There's no logarithms. So there's no real restrictions on the domain. So the domain would be all real numbers. Another example is the absolute value function. If you plug in 5, you get 5. Remember, it doesn't change the number, but if you plug in -3, it just changes the negative to a positive. We haven't done that in a while. But regardless of any of that, there are no fractions with variables in the denominator. There are no square roots. There are no logarithms. So you can plug in any input as long as it's a real number. You're going to get an output. So the domain is all real numbers. So go ahead and try number 34. And I want you to think about why the domain of this function is all real numbers. Write your reasoning, and when you come back, we'll do it together. Alright, we're back. So the function has no square roots, fractions, logarithms, or other things that might restrict its domain. Doesn't matter what you plug in to that function, as long as it's a real number, you're going to produce an output. So the domain is all real numbers. I know these problems are kind of easy because you already know what the answer is. But number 35 is not going to be quite as easy to figure out, but see what you can do with that problem. And when you come back, we'll do it together. Alright, we're back. So again, this function has no square roots, fractions, or logarithms, or other things that might restrict its domain. And you might say, well, wait a second, what if we plug in -3? Then we'll get 2 to the 0 power. Well, we know 2 to the 0 power is equal to 1, so that's fine. What if we plug in -5? We'll get 2 to the -2 power, but that's okay because that just equals 1 over 4. If you plug in a fraction or anything really, it'll produce an output. So I know that example was a little bit more difficult, but again, the domain is all real numbers. So sorry I gave you kind of a hard one there. But if you got that answer, good job. Now I want you to understand very clearly, and you probably already noticed this, it's kind of a pain to have to write the domain in words every time, especially when you have to write a long sentence. But the good news is that we're not really going to have to do that for the rest of the math curriculum. We're going to use abbreviated notation. There's actually 3 ways to write the domain of a function. Words, which is what we've been using so far, but also something called set notation, which is much easier to write, much faster. Or we can use interval notation, which is also much faster. And here's a bunch of examples of interval notation and set notation. But I'm not going to go over every example there. It's better just to get into problems. Let's do an example problem. It says here, write the domain of each function using interval notation. So we're going to start out with interval notation. Now, the domain of this function is already written in words. So we don't really have to pay attention to the actual function itself. All we're going to do is translate from word form to interval form. So how do we write the domain, all real numbers between 100 and 700, in interval notation? Well, all we do is draw parentheses and then 100, comma, and 700. So it looks like coordinates. Now you're probably thinking, wait a second, again, these are coordinates. Why are we writing coordinates? Well, mathematicians like to use this notation for intervals as well as coordinates, so it gets kind of confusing. Why do they do that? I don't know. It's just tradition. But these are not coordinates. If you draw a set of axes and plot these numbers, then yes, they become coordinates. But in this case, this is just interval notation. Now, it's very important to understand that you cannot write 700 first, then 100. The smaller number always goes on the left. When it comes to interval notation, this actually has no meaning. Never write the bigger number on the left. In the English language, remember, we always write left to right, and so it makes sense that we start with the smaller number and then get bigger, I guess. But that's it. That's all you have to write. Notice that that's a lot easier to write than word form. This takes about 5 seconds to write that, and you're done. The reason it's called interval notation is because it describes an interval, 100 to 700. So let's try number 37. Again, we have the domain written in words, all real numbers between -4 and 6, including -4. So we're going to use, again, 2 sets of parentheses, and we're going to go from -4 to 6. And that's it. It's that simple. But we have one issue. Notice that it says including -4. So how do we write interval notation that tells us that our domain is not just the numbers between -4 and 6, but it also includes -4? How do we do that? Well, what we do is we change this parenthesis to a bracket. That means all the numbers between -4 and 6, but including -4. So we can plug in -4 for our domain, but we cannot plug in 6. Let's try another problem here. It says all real numbers between 0 and 9, including 9. So again, we write 0, 9 with parentheses, but instead of a parenthesis on the 9, we write a bracket. And again, I'm going to say this over and over again. Be aware, the smaller number comes first. -4 was the smaller number up here. That comes first on the left. And 0 was a smaller number on the next problem. So that number comes first. The smaller number is always written at the left when it comes to interval notation. If you write 9, 0, that has no meaning with interval notation. All right, let's do one more of these problems before you try one on your own. All real numbers between 8 and 20 inclusive. So that means that all numbers between 8 and 20, they're part of the domain, but both 8 and 20 are also part of the domain. So what we do is we write 8 and 20, but we write brackets on both those numbers. again, notice that the smaller number was written first. You must write the smaller number first. So again, this describes an interval. It says all numbers between 8 and 20, but we put closed dots if you want to use number line notation to show that 8 and 20 also are part of the domain. So I want you to try number 40. You can use numbers 36 through 39 to help you. And when you come back, we'll do it together. All right, we're back. All real numbers between -10 and 87 is the domain. So in interval notation, that's just going to be -10, 87. But notice it doesn't say inclusive, and it doesn't say including -10 or 87. So you put parentheses instead of brackets. So if you got that answer, good job. Try number 41, and when you come back, we'll do it together. All right, we're back. All real numbers between 6 and 24, including 24, is the domain. So we write 6, 24. The smaller number has to go on the left. And because it's including 24, we put a bracket on 24. This means that the domain is all numbers between 6 and 24, not including 6, so we put an open dot if you want to use the number line notation, but including 24, so we put a closed dot. You don't have to draw the number line if you don't want to. So if you got that answer, good job. Go ahead and try 42. When you come back, we'll do it together. All right, we're back. All real numbers between 243 and 384, including 243, so we put a bracket on 243. Remember, put your smaller number at the left. The smaller number always comes first at the left. So if you got that answer right, good job. Go ahead and try number 43. And when you come back, we'll do it together. All right, we're back. All real numbers between -7 and 36 inclusive. That means that our domain can be all numbers between those, but also including the endpoints, -7 and 36. So we write brackets on both those numbers. So if you got that answer, good job. So now we have logarithms, and the domain is written in words. It says all real numbers greater than -7. So how do we write this in interval notation? Well, we say we write -7, infinity. Now this is the first time in my curriculum that we've seen the infinity symbol. It's just an 8, and then you turn it on its side. So it's an 8 laying on its side. That means all numbers greater than -7. So we put an open dot, so it can't be 7, but all numbers to infinity, all numbers bigger than -7. So infinity is not really a number. It's just a concept. It just means you can put any number greater than 7. Now, we never write a bracket on an infinity symbol for the reason that I just explained. You can't say that a number is equal to infinity, because infinity is not a number, it's just a concept. So you always put a parenthesis on infinity. And in this case, our domain cannot be, our inputs cannot be equal to -7, only greater than, so we put a parenthesis on -7. So here we have another example. It says all real numbers less than or equal to 5. Now, in this example, we're going to write -infinity, 5. And we always put a parenthesis on an infinity symbol. And it says less than or equal to 5, so we need a bracket, so our inputs can be equal to 5. So what this means is that, again, your domain can be any number equal to 5 or less than, so that's why we put a negative. Our bound is -infinity, even though infinity, again, it's not really a number, so it can't be a bound. It's just a concept. Now notice, again, we put the smaller number at the left. Infinity is not really a number, but you get the point. It's these smaller numbers, our interval goes from 5, and then all numbers in the interval are going to be smaller than 5, so we put the 5 at the right because it's the biggest number in the interval. Okay, number 46, all real numbers less than 32. So again, it's just the same situation, but it doesn't say equal to 32, so we have to put a parenthesis on the 32. 47, it says all real numbers greater than or equal to 1. So we're going to start with 1 because that's the smallest number in the interval. And we need a bracket because it says greater than or equal to. And then it just goes on and on and on. So we need the concept of infinity. So we write an 8 on its side. Now here's an example where the domain is all real numbers. So how do we do that? Well, with interval notation, we say negative infinity, comma, infinity. That just includes all numbers, all real numbers. So I want you to use numbers 44 through 48 to help you with number 49. Go and attempt 49, and when you come back, we'll do it together. All right, we're back. All real numbers greater than 0. So that's going to be 0, comma, infinity. If you got that answer, good job. Go ahead and try number 50, and when you come back, we'll do it together. All right, we're back. All real numbers greater than or equal to negative 1/2. So it can be equal to negative 1/2, so we have to write a bracket and then an 8 on its side for infinity. So if you got that answer, good job. Try number 51, and when you come back, we'll do it together. All right, we're back. So negative infinity to 8 is the interval. So again, that means your inputs can be anything less than 8. So we go to infinity in the negative direction. So because 8 is the biggest number, it goes at the right, and all other numbers are going to be smaller, so the negative infinity goes at the left. Remember, the smaller value always goes at the left. In this case, not really a value, mainly just a concept. Now go ahead and try number 52, and when you come back, we'll do it together. All right, we're back. All real numbers greater than or equal to 0, so that's going to be the following. If you got that one right, good job. Try number 53. When you come back, we'll do it together. All right, we're back. This is a special situation. It's just going to be negative infinity to infinity. So if you got that one right, good job. Okay, now our domain is all real numbers between 4 and 8 or between 9 and 13. So this is going to be something different. We have to use what's called a union symbol. We're going to say the interval between 4 and 8, and then we're going to use this U symbol, which is a symbol that basically means or. Our inputs can be between 4 and 8, or our inputs can be between 9 and 13. Now I know what you're thinking. You're thinking, I don't like that. I don't want to have to remember another symbol. But this is just one of the typical symbols you're going to see in interval notation, and you're going to get used to that as you use it more and more. So again, that means that our inputs can be any real number between 4 and 8 or between 9 and 13. Our inputs can't be both between 4 and 8 and 9 and 13. That's impossible for a number to be between 4 and 8 and 9 and 13 at the same time. But the number can be in one or the other interval. That's why we say the union symbol or. So now our domain is all real numbers between negative 8 and negative 3, including negative 3, or all real numbers between negative 2 and negative 1. So we write the same situation with a union symbol. No difference whatsoever, except it says up here, including negative 3. So in the previous problem, we wrote parentheses, but here we have to change that parenthesis to a bracket because our domain includes -3. So again, we're learning how to use the union symbol with these problems because we have multiple intervals with a gap in between the interval. So now our domain is all real numbers between -5 and 3, including -5, or all real numbers between 8 and 7, including 8. So again, it's the same situation. We have an interval between -5 and 3, or we have the interval between 8 and 17, but we have to change some of those parentheses. We have to change the parenthesis on the -5 to brackets, and the parenthesis on the 8 to a bracket. So again, this means that our inputs are all numbers between -5 and 3, but including -5 and not including 3. Or the interval between 8 and 17, including 8, but not including 17. All right, this problem says all real numbers between 4 and 12 inclusive, or between 13 and 15 inclusive. So it's the same situation. We have this interval, or we have this interval, and it's not just the numbers in between those numbers, but the numbers themselves. So we have to write brackets on both these. All right, so I want you to try number 58. Use numbers 54 through 57 to help you. And when you come back, we'll do it together. All right, we're back. So this is going to be the interval -5 to 7, or the interval 10 to 23, but not including those endpoints. So we don't use brackets. If you got that answer right, good job. Be sure to use your union symbol. Again, the union symbol means or. This interval or this interval. So try 59. When you come back, we'll do it together. All right, we're back. So the interval -12 to -10, or the interval from 0 to 4, and it says including -12, so we put a bracket on that, and parentheses on everything else. If you got that answer right, good job. Go ahead and try number 60, and when you come back, we'll do it together. All right, we're back. So we have the interval 5 to 7, or 9 to 12, 11, including 9, so we put a bracket on 9, and including 7, so we put a bracket on 7. So if you got that answer right, good job. Go ahead and try 61, and when you come back, we'll do it together. All right, we're back. All real numbers between -8 and 4, inclusive, meaning both those numbers can be in the domain, or all numbers between 6 and 37 inclusive, so brackets on both those numbers. If you got that right, good job. So for 62, it says all real numbers except 4. So this is going to require infinity symbols. So what we do is we say the interval -infinity to 4 with parentheses, or the interval from 4 to infinity. So what that means is any number less than 4, but then when you get to 4, we put an open dot, meaning 4 is not included in the domain, and then we go from 4, we can go to positive infinity. So we have this interval, and we have this interval. So two intervals. And again, we write parentheses always on the infinity symbol. We write parenthesis because it's impossible for a number to be equal to infinity. And we don't want our input to be 4. So remember, if you put a parenthesis on 4, that means 4 is not included in the interval. So I know this seems kind of complicated, but that's how you would write all real numbers except 4 with interval notation. Let's try one more of those. This problem says all real numbers except 0. So we say negative infinity to 0 or 0 to positive infinity. Okay, so I want you to try 64. I know these problems are a little weird, but try 64, and when you come back, we'll do it together. Alright, so we have the interval negative infinity to 5/9 or 5/9 to infinity. So what this means is that our domain is all real numbers except 5/9. It looks kind of complicated to write it in interval notation, but that's what it would look like in interval notation. Our numbers for our domain can be anything in between negative infinity and 5/9, and anything in between 5/9 and positive infinity, but it can't actually be 5/9. Try 65, and when you come back, we'll do it together. Alright, we're back. So now we have negative infinity to negative 10. Make sure you write a parenthesis and not a bracket. And negative 10 to positive infinity. So if you got that one right, good job. So that's interval notation. As you can see, it's much quicker to write interval notation, but we have to learn a different type of notation called set notation. And you might say, well, wait a second, we just learned interval notation. Can't we just use that? Why do we have to learn a different type of notation as well as interval notation? The answer is this is just something that mathematicians use commonly, so unfortunately we have to learn two types of notation. You're going to see this in the math curriculum, so you need to be able to recognize it. So here we have the domain stated in words, all real numbers less than or equal to 5, and we're going to convert that to set notation. So here's what it looks like. We're going to draw two braces. These are called braces. And then we're going to write an X in a vertical line. And then we're going to write our restriction for the domain. X must be less than or equal to 5. That's it. That's set notation. Now I know what you're thinking. You're thinking that looks really weird. Where did you come up with that? Well, it's just a language that mathematicians use, and let me translate this language for you. What this means, if you were to say it in words, it means the set of all x such that x is less than or equal to 5. That's why it's called set notation. All real numbers less than or equal to 5 is a set of numbers. So you can call it a set. So that's why they call this set notation. When we're talking about interval notation, it's describing the intervals on a number line that the domain can be. But you can also describe it as a set of numbers. So again, this translated means the set of all x such that x is less than or equal to 5. So you write the variable that you're using. Again, the inputs are almost always written as x values. Then you write a division line there, and then you write the restrictions on your domain. That's how that's how set notation works. So now it says all real numbers greater than -7. So we say the set of all x such that x is greater than -7. And you always write two braces at the left and the right of your notation. So it's that simple. Let's go on to 68. It says all real numbers less than 32. So we write two braces. Now we write our x, our variable that we're using for the input, which is almost always x. You can see that it's up here. It's x. And we write a division symbol. And then we write our restriction. X must be less than 32. So number 69, the domain is all real numbers greater than or equal to 1. So we say the set of all x such that x is greater than or equal to 1. Alright, and number 70, this is kind of a special problem. The domain is all real numbers, but set notation actually doesn't work in this case. It's just traditional in this example to just say all real numbers. So we don't really use set notation to describe all real numbers because there are no restrictions to write here. So traditionally we just say all real numbers whenever we're writing set notation, or we're asked to write set notation in that example. So I want you to try number 71 using 66 and 66 through 70 to help you. So go ahead and try 71. When you come back, we'll do it together. Alright, we're back. So we write two braces here, and then an X and a vertical line, and then we write our restriction. X must be greater than or equal to -1/2. So if you got that answer, good job. Try number 72, and when you come back, we'll do it together. Alright, we're back. All real numbers greater than 0, so it's the set of all x such that x is greater than 0. So you write two sets of braces, or one set of braces that is, and then you write x in a vertical line, and then your restriction on x. It must be greater than 0. So try 73, and when you come back, we'll do it together. Alright, we're back. So again, two braces, your x, a vertical line, and then your restriction on x. So if you got that answer right, good job. Try number 74, and when you come back, we'll do it together. Alright, we're back. All real numbers greater than or equal to 0. So we say the set of all x such that x is greater than or equal to 0. And then an end brace. I'm not very good at drawing braces. Alright, go ahead and try number 75. And when you come back, we'll do it together. You want to use number 70 to help you on that one. Alright, we're back. So again, set notation doesn't really work with this example, so you can just write all real numbers. Okay, in this case, so the domain is all real numbers except 0. So for set notation, we write the set of all x such that x is not equal to 0. Now this is kind of strange because this notation here is telling us that x can be everything, every other number except 0. If you just write x not equal to 0, that's the only restriction on x, is that it can't be 0, but this assumes that x can be every other number. So it's kind of a strange way to write the domain. Down here it says all real numbers except 4, so we say the set of all x such that x cannot be equal to 4, but again that assumes it can be every other value. I know that's kind of strange, but why don't you try 78? Use 76 and 77 to help you, and when you come back, we'll do it together. Alright, we're back. So you want two braces, an x, a vertical line, and then x cannot be equal to 5/9. That's the only restriction. Assuming that you know, in this notation, again, we can never use imaginary numbers with set notation. It's always assumed to be real numbers. So the only restriction that you need to write is that x cannot be equal to 5/9. Go ahead and try 79, and when you come back, we'll do it together. Alright, we're back. So the set of all x such that x cannot be equal to negative 10. So if you got that notation written correctly, good job. So let's try number 80. It says all real numbers between 100 and 700. Sorry, the computer program is jumping around. It's got some glitches in this OneNote program that Microsoft has not fixed in a long time. All real numbers between 100 and 700. So we say the set of all x such that x is between 100 and 700. Remember, this notation means that x is between 100 and 700. It's greater than 100 and it's also less than 700. You have to use the word and because both these inequalities have to be true at the same time for this particular expression. But these are not less than or equal to symbols, so x cannot be 100 or 700. So again, it's the set of all x, the set of all x such that x is between 100 and 700. Number 81, it says all real numbers between negative 4 and 6, including negative 4. So we say in set notation the set of all x such that x is between negative 4 and 6, but it's also including negative 4, so we have to change this less than symbol to a less than or equal to symbol. So again, you're talking about a set, you're identifying your variable, and then you're putting a division mark, and after the division mark you write your restriction on x, your inputs. Number 82, all real numbers between 0 and 9, including 9. So again, the set of all x such that x is between 0 and 9, but including 9, so we write a less than or equal to symbol on the, or next to the 9. Okay, number 83, all real numbers between 8 all real numbers between 8 and 20 inclusive. So the set of all x such that x is between 8 and 20, but we're including both 8 and 20, so we have to put less than or equal to symbols. We have to write those for both symbols. So I want you to try number 84. Use numbers 80 through 83 to help you, and when you come back, we'll do it together. All right, we're back. So the set of all x such that x is between 87 and negative 10, and an end brace. If you got that answer, good job. Go ahead and try 85, and when you come back, we'll do it together. All right, we're back. So the set of all x such that x is between 6 and 24, but also including 24, so we have to change that inequality symbol to a less than or equal to symbol. So if you got that answer, good job. Go ahead and try number 86, and when you come back, we'll do it together. All right, we're back. So again, we use two braces, and then x in a vertical line, and we say that x is between 243 and 384, but because 243 can be part of the domain, we write a less than or equal to sign next to 243. So if you got that answer right, good job. Go ahead and try number 87, and when you come back, we'll do it together. All right, we're back. All real numbers between negative 7 and 36 inclusive. So we say the set of all x such that x is between negative 7 and 36, and we write less than or equal to symbols for both those inequalities. So if you got that answer right, good job. All right, on to the next problem. So now our domain is all real numbers between 4 and 8, or between 9 and 13. So in set notation, this would be the set of all x such that x is between 4 and 8, or, very important that you use the word or, x is between 9 and 13, and then of course end bracket. Let's try one more of these before you try one on your own. All real numbers between -8 and -3. So the set of all x such that x is between -8 and -3, but it says including -3, so we have to put a less than or equal to symbol. So it fits that description, or x is between -2 and -1, and of course end bracket. Okay, so you can use 88 and 89 to help you with number 90. Go ahead and try number 90, and when you come back we'll do it together. Alright, we're back. So we want the set of all x such that x is between -5 and 3, but including -5, so we have to put a less than or equal to symbol next to the -5, or our domain includes all numbers between 8 and 17, and of course end bracket, but it says including 8, so we need a less than or equal to symbol next to the 8. So if you got that one right, good job. Go ahead and try number 91. Remember, inclusive means both numbers and the interval are included in the domain. So try 91, and when you come back we'll do it together. Alright, we're back. So the set of all x, my braces are kind of starting to look weird. The set of all x such that x is between 4 and 12, or x is between 13 and 15, and it says inclusive for both of those, so we need less than or equal to symbols for all of those inequalities. So remember, inclusive means both numbers are included in the domain. So if you got that one right, good job. So that is the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and number 3 and number 4 and number 5 and number 6 and number 7 and number 8 and number 9 and number 10 and 11 and 12, 13, number 14, number 15, and number 16, and number 17. But don't go before you get your homework. Let's take a look at the homework. Here's screenshot number 1 of the homework. And here's the answers for the homework. Remember, if you don't do that homework, it's a 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.